Hello, this is Jacob Hawkins, and I'm presenting on our fourth interactive advanced concept presentation for general chemistry. This week in class, we've been talking about thermodynamics. So covering some basic terms, thermodynamics, really broadly speaking, is a study of heat, and thermochemistry is a study of heat that's involved in physical and chemical changes. So heat itself is a type of energy. We can call it thermal energy, which is energy transfer as a result of temperature differences between a system and its surroundings. So what do those two words mean? So a system is the thing that we are either observing or trying to act upon. So if we're taking the example of a chemistry lab, let's say we're doing an experiment where we're trying to raise the temperature of water. The system might be a beaker of water. And then the surroundings are everything else that's in the lab. So that would include the Bunsen burner that we're using to add heat to the system. It would be the atmospheric pressure of the room. It's everything else. So heat can be expressed mathematically in the equation Q, which is heat transfer, equals MCAT, which is the product of mass of a substance multiplied by its specific heat multiplied by its change in temperature. And specific heat, just in case we're not aware, is the amount of energy that's needed to change the temperature of 1 kilogram of a substance by 1 degree Celsius. Heat is also always, well, not always, but it's typically expressed in units of joules, which are the amount of energy needed to raise the temperature of a given mass by 1 degree. So if you're looking at equations that in any way, involve thermodynamics, you're probably going to be using joules. Other important concepts with thermodynamics, probably principal among them, are the first law of thermodynamics, which states that energy cannot be created or destroyed. To say this another way, the energy of the universe is at a constant. So this means that energy going into a system has to originate from its surroundings and vice versa. So you can't just make energy out of thin air, and you also can't get rid of it. It has to come from somewhere, or you have to move it to someplace else. So again, to express this in an equation, that would be the sum of the change of energy of a system with the change of the energy of its surroundings will always be zero, because it has to go in one direction or the other. So you're putting energy into a system, and that has to come from its surroundings. Or if the reverse is happening and the system is putting energy into the surroundings, it's coming from the system and it's moving in that reverse direction. Another important concept in thermodynamics is conduction. So thermal conduction is the process by which heat is transferred via collision of nearby atoms or molecules. So I have here an image of the different states of matter. So we have solids, liquids, and gases. So let's think about that in terms of a solid. So you see that with solids, the molecules are very snugly fit together. They're kind of packed in there. So if you're exposing those molecules on any end of the system to thermal energy, those will start to get those molecules hitting up against one another. And because they're so tightly packed, that domino effect will happen quite quickly and almost cascade across the rest of the system very rapidly. Liquids kind of operate in the same way. They're packed together. They're not quite as packed as tightly together as a solid. But still, they're very close. So when you start to excite one end of it, that heat energy will very quickly spread across the rest of the system. Gas, on the other hand, we see here those molecules are quite spread apart, and they certainly can be in real life. So you can imagine that a gas is not going to conduct heat as well as a solid or a liquid, right? Because it's going to take a while for those molecules to bump up against one another and for that energy to then spread across the rest of the system. So this will definitely become important because we're now going to go over an experiment that I did where I took balloons, one which was filled with gas and then another that was filled with liquid. And I wanted to see which one of those would essentially withstand heat. So I was quote unquote fireproofing a balloon. So the next slide will be that video, and then on the last slide we'll kind of discuss that experiment and close out the presentation. Hello everyone, this is Jacob Hawkins, and I'm presenting on our fourth interactive advanced concept presentation for General Chemistry 1. So this week in class we're talking about thermodynamics and thermochemistry, and our assignment for this week is to demonstrate some of those concepts by making a fireproof balloon. So what I'm going to do is I will first fill up just a regular balloon with air, I'm going to expose it to fire and see what happens, and then we'll do the same thing with our fireproof balloon, which is fireproof in the sense that it contains water, and we will see what the difference is. So I have one regular balloon. I'm going to fill it up. Okay. Okay, so this is our non-fireproof balloon, and I have our fire source here. So the instructions are just to hold the balloon right over the flame. Okay, and right away it popped, so that is not fireproof. So now we have our other balloon, which I, just for the sake of time, have filled up with water just from the kitchen sink, and we're gonna see what happens again when I expose it to flame. So as you see, nothing. So it is effectively fireproof. I'm a little hesitant to get this too close to my phone, but just to show a little bit more of a close-up, you can see there I am, getting the flame close enough that it's blackening the, the balloon itself, but it's not popping. So just to kind of show, if I kind of expose the balloon to the, the heat more up top here where there's actually air and there's really not any water, we'll just see what happens. Oh, actually not even that. So maybe there's more water in here than I thought. When I did it previously, there was some air at the top, and when I did that, it popped and it got water everywhere. So that is it. So that is a fireproof balloon. So on the final slide, we will kind of discuss, what's going on here and why I was able to expose that water balloon to heat without it bursting. All right, so let's break down what we saw there. So obviously the water balloon was able to withstand a lot of heat, whereas when I put the flame up against just the conventional balloon filled up with air, it burst right away. So why did this happen? So the first thing I want to say is that thermal energy is a type of kinetic energy. And what I mean by that is thermal energy and its ability to move across a system is completely dependent on the molecules of that system and their proximity to one another and their ability to collide with one another. So like I said on a previous slide, liquids are more conductive than gases. The reason being is that liquids are more closely packed together, and their molecules are able to collide with one another much faster than gases that are more spread out. So thinking about that, it would make sense that the water balloon was not popping, because even though we're putting that flame right up against the plastic and you might think that it would just melt right away and then burst, actually the heat was being absorbed so quickly through that thin layer of plastic and then being moved across the system. Whereas with the balloon that was filled up with my breath, gas is much slower to conduct heat. So it allowed time for that heat to kind of sit at the plastic, causing it to melt and then the whole thing to burst. So this was an interesting experiment. It was definitely, I'm glad I didn't get water everywhere all over my apartment. So I'm glad that the water was a good conductor of the heat. But I did learn a lot. It was helpful to kind of take these thermodynamic concepts and apply them to a real world example. And I hope that other people might have learned something, and I look forward to watching everyone else's presentations.